Morning. Here we are once again. It's the physics video lecture, Physics 2A, video lecture 13. I'm going to start off with a homework assignment that somebody asked me about. And if you want to see homework assignments done at the whiteboard here, go ahead and let me know in the emails. This was problem 10 of chapter 3. So homework chapter 3, problem 10. And the question was to find the angle at which a launched projectile, so let's suppose we have a certain angle here, theta. We know the projectile has a range and a maximum height on our x and y axes respectively. It has a range and a maximum height, and there's a certain angle for which the maximum height is equal to the range. Okay. So let's go ahead and just write y maximum is equal to range, and the maximum height, I'm just going to write the formula down. You guys should be able to figure this out. The maximum height would be v0 sine theta squared divided by 2g. This is something you can get out of our kinematic formulas, because this was v sub y, the quantity squared, right? We've got a v0, v sub y is the y component, v0 sine theta, squared divided by 2g. Get that out of our vertical throw type of kinematic problems. Over here on the right side, we have v0 squared, actually 2 times v0 squared, sine theta cos theta. I had derived this formula as well, divided by g. So you see there are some great cancellations going to come in. We're going to have v0 squared on both sides. We're going to have g on both sides. And sine theta divided by 2 is equal to 2 sine theta cosine theta. So that gets rid of one of the signs on each side. And now we'll divide sine theta by cosine theta on the left. By cosine theta both sides, we get tangent theta on the left. Cross multiply over, that's supposed to be a theta here, theta. And cross multiply over, we get 4. So theta is the inverse tangent of 4. Pretty interesting problem, right? I'll leave the rest of it. That was the interesting part. And what else is on our agenda today? Quite a bit. So let me go ahead and make a little list. Today, we're going to start out with friction. We've already had some definitions and homework problems on it. I have a couple important things to show you about friction. Then two-body problems. And if we have time, we'll also do fall with friction. And that's going to wrap up chapter 4, and next time we'll be going on into chapter 5. Good. So let's talk about friction a bit. This time I'm going to lead off with a demonstration. So what we have here is a board that has 4 different materials on it. There's rubber, there's kind of sandpaper, and some kind of wood, and that's some kind of plastic here. And we have 4 brass pucks here, little brass squares. I'm going to place them all up here. Actually, I'll just do one at first. So the point is that we increase the angle, and eventually it slides down. Okay. And it's going to be different with different materials. It's always brass against something. So brass against plastic, wood, sandpaper, and rubber. And I'm going to tip it up slowly, and it's sort of a race to who survives, okay? So the plastic was that slippery. You notice there's an angle at which the puck just slid down. Okay? So let's keep going up here, increasing the angle. Okay. That one started to go. I declare an unfair race. Actually, the principle is good, but that sandpaper itself isn't uniform anymore. Maybe we should disqualify the sandpaper. Let's try this again. Okay. Oops, okay, once more, here we go. Plastic, so there is a definite angle at which the brass slid down the plastic. Here's the second angle for the wood, and the rubber are about the same. Sandpaper is the winner after all, okay? So what we're going to do is analyze that. We did that construction with the inclined plane on the board last time. So let's go ahead and look at this. We have our incline. Always draw these things pretty generously. Okay. Gravity pointing down. I'll just indicate it like that. So now we have this brass puck. It has some mass M. And the force is on here. Take another color. There is the weight. And there is the normal force. And there is a force of friction. Okay. So this we're going to call mg. This one we're going to call n. And we know that the law of friction is that the frictional force is a coefficient of friction times the normal force. So we're going to do the same coordinate system we had last time. I'm going to go ahead and put x and y parallel and perpendicular to the incline because it's convenient. And now we have, remember we have this habit, we're trying to generate or get this habit F net equals MA. But this time we're looking at the critical angle, or call this alpha. We're looking at the critical angle at which this thing just begins to slide, okay? So alpha equals a critical angle at which the mass begins to slide. Begins to slide. Okay. So that was our demonstration right there anyway. So I'll put demonstration here as well. Good. So we're doing the x components, and the x component is mu times n pointing uphill. And then we had last time, I'll do this again. We had alpha, so pointing downhill here, this one right there is minus mg sine of alpha. And because it's not moving, this equals 0. Okay. The y component, we have, and this is what we had last time as well, we had n minus mg cosine of theta is equal to 0. Okay, these are these two components. My red vector there, mg sine theta and alpha, make up my mind, right? mg cosine alpha. Okay. That was that part and that part there. So make sure you recognize and understand the analysis of this triangle. And what we're going to do is take n from equation 2 and plug it into equation 1. So that gives us, for our analysis, mu mg cos alpha. Okay, I'm taking this, solve it, bring it into there, minus mg sine alpha is equal to 0. We get a great result out of this, because what we're solving for is that coefficient of friction that we had on the friction race. So let's go ahead and put that up. Mu is equal to, notice the masses and g both cancel, so it's just going to be alpha, here let's write it down, sine alpha over cosine alpha. So this is a way of measuring the coefficient of friction. We could have had 4 different coefficients of friction, and it would have always been the brass between whatever it's touching, whatever it's on. So make sure when I do a calculation like this that you're able to sit down, put it to the side, and repeat it. Okay, you want to repeat this calculation. This calculation is just as good as a homework problem. In fact, it may very well be on one of the homework problems. So this is a way to measure this coefficient of friction. And you'll notice tangent of alpha is a dimensionless quantity, mu is a dimensionless quantity, so everything worked out the way it was supposed to. Good, so that's the way you can get a frictional coefficient. Now that frictional coefficient is also in play in a horizontal motion, and here I'll just make my point this way. We'll slide the whole can across the table. Okay, so there's a frictional coefficient between, say, the surface of the table that we would measure with the angle and all, and then we know it, and we can send this thing across the table and it comes to a stop. That's just friction. So let's do these dynamics. I send this thing across the table. It went a meter, it had so and so much speed, came to a stop. And I think this is one of our homework problems. Due at the end of the week, but I'm glad to do it right now. Unlike the book, I'm not plugging any numbers in, and you'll see that's better. As I've said before, you guys, as far as possible, you want to solve the problems with no numbers, just symbols the way I did here, and put the numbers in at the very end. So let's call this example, this friction example, you know, a car locks its brakes and comes skidding to a stop, for instance. Car skids to a stop. And draw our funny little picture. So here's our car, let's let it be a truck. Okay, it's moving along, and it's going to come to a stop. Hit the brakes right here. How long does it take to come to a stop? And the car has initial speed v0. Okay. So as soon as the car slams on the brakes, there's just friction. I'll use this same picture to draw the forces on the car now. It has mg, it has a normal force and there's a friction force equals mu times m. Okay, there's our Newton's law free body diagram again. And what we want to find out is, given this initial speed v0, frictional coefficient mu, how far does it go? How long does it take to come to a stop? So just to follow my own rules, I'm going to write F net equals ma. Okay. Now the question is there acceleration this time? Absolutely. It's going to be slowing down, it's decelerating, it's an acceleration in the left direction. We can call this the x direction. So in the x direction we have minus mu n, and that's it. Left side of our Newton's law here, let me write that little meter just to make sure we see everything. So we're doing the net force equals mass times acceleration. We're doing the x component, we say it's minus mu n. That's the only x component, so that equals m times a sub x. Okay. Now we're going to do the y component, and there we see we have n minus mg equals 0. So we can combine these two equations and solve for the acceleration. A equals minus mu n divided by m, so I solve for the acceleration, equals minus mu over m. And what do we have here? For n, we just have mg, bring that over the other side. That's mg, m's cancel. So I'll go ahead and showcase this. Right here we just found acceleration is equal to minus mu g. Okay, so what are we going to do with this? We have an initial speed and we have an acceleration. Now I'm going to bring into play the kinematic equation. Go ahead and erase a little here. In fact, you should always have your kinematic equations in front of you on a piece of paper. You know, you should build a nice formula sheet with the important ones handwritten so that you recognize them. Kind of thing you can't repeat too often. So you've got your formula sheet out, and I'm going to write it up on the board right now, and let's see what happens. Okay. So let's put down the kinematics in one dimension. So we have x equals x0 plus v0t half at squared, v0 plus at, and this third one is the one we're looking at, v0 squared plus 2a x minus x0. So we're going to use this third equation here. Remember, what we're trying to find is how far do we come? How long till we take a stop? How far until we come to a stop? Yeah, we should have some words up there to that effect on this board here. So you guys go ahead and fill that in. So here, A is equal to minus mu g, and V final equals 0. X minus x0 is the distance we're looking for. So x minus x0 equals, I'll go ahead and solve first, equals v squared minus v0 squared over 2a. And that means d, which is what we're looking for, this is a 0, equals minus v0 squared divided by 2 times a, divided by 2 minus 2 mu g. equals 2 times mu times g. Okay, there's a great answer. This one we also want to showcase. So here's the distance traveled. V squared over 2 times mu times g. This is the kind of formula that you want to have in its general form. Here's a 0, by the way, initial speed. This thing is rich in content. Now watch this. First of all, we learned something about the initial speed, and that is, given some coefficient of friction, it's proportional, the distance proportional to the speed squared, okay? As a car driver, this is very important. Suppose you're going 30 miles an hour, and it takes you a certain distance to come to a stop. If you're going 60 miles an hour, it would be 2 times 30, so the square of that would mean it's 4 times the distance to stop, okay? If you double your speed, you quadruple the distance to stop. If you triple your speed, you need 9 times the distance to stop. And this is a law of nature. You may have tripled your speed and now you really, really want to stop, but it's going to take 9 times the distance, okay? So that's the first thing. So this analysis of this thing, you guys should be filling in some of these words here, okay? We double the speed, we quadruple the distance. The other thing that's interesting is the frictional coefficient in the denominator. Because you can see if this friction goes to 0, you will slide an infinite distance, okay? So you can see if the friction is half as good, you're going to go twice the distance and so forth. So all of these insights are only available if you analyze this formula here. There's a big difference between just a pure mathematics class. We're doing math all the time, but after we get our answer is when the real insight begins. Can't stress that enough. So what should we say here? Well, I said it. You guys write it down. Quadratic dependence on the initial speed and this inverse dependence on the coefficient of friction. Okay. So that's a good problem. The problem with the I think somebody's sliding down a hill on a sled that I assigned last time is essentially this problem right here. Okay. So always try to do the problem with no numbers first. Numbers are just for the end. Good. What else is on our plate? Let's see how much time we have. Yeah, we're doing fine. Okay, let's see. I wanted to talk about two-body problems now. So we've talked about friction pretty thoroughly, and I'll assign a couple of problems with friction in the homework. We've already done a couple, maybe friction on an incline as well. So next, two-body problems. Now these bring into play Newton's third law. So let's have a look at Newton's laws once again. Okay, so two-body problems. And we have Newton's laws. The first one, I'm just going to write inertia. The second law, net force equals mass times acceleration. You know, we're already seeing all kinds of interesting applications. The third law is the one we're also going to have to bring into play. It's that the force of one body on a second is equal and opposite to the force second body exerts on the first. So that's a good shorthand for it. It's vector minus sign in front, so equal and opposite. Now the example that I want to show, this is one we have a lab on. You'll see a number of problems like this in the problem sets, and I'll hope to convince you that this is a very important problem, even though it looks very basic. So we have a tabletop. We often have a lab tabletop, maybe a frictionless track, maybe a surface with friction, but I'll put little wheels here. And this is our M1, and what we do is we connect it via a string to a second mass M2. So we're going to start with no friction in this problem. No friction. It's the most important case. And what's going to happen here, well, M2 is going to drop and pull M1 across the table. It's that simple. And apparently they're moving together, and this string isn't going to stretch. The pulley is really lightweight plastic, massless pulley. The string's not going to stretch, so as M2 accelerates down, M1 accelerates forward. Okay, so let's first of all draw we'll just write Newton's law down. But the first thing we'll do is the free body diagram. And what we have here, M1G and N, we could also put a friction pointing to the left, opposing the direction of motion. Next time. Now we also have M2G. And you would think that, there's a string here, you'd think that the tension in the string is just the same as the force pulling down on it. But as soon as things start moving, that's not the case. So we have to label a tension here, okay? And here's where Newton's third law comes into play. This tension is what's acting on M2, and this same tension here is what's pulling M1. So these two tensions are the same because it's a massless string. That's by Newton's third law, right? These are, so to speak, equal and opposite forces because the positive direction changes from forward to down. Okay, they're equal and opposite. So it's pulling, this is pulling back. So this is what we're going to set up now. And we're going to find the tension and the acceleration. I'd leave those up there, who knows, we may need them. Yes, so Newton's laws, and we're going to do mass 1, and mass 1 has in x direction t is the only x direction vector equals m1 times acceleration. In y direction we have n minus m1g equals 0. In this problem, this one's not going to play a role. If we had friction, we would have to build this one in as well. Mass number 2, what do we have? We only have the y direction here. But as far as the symbols go, and this is really crucial now, we have minus t plus m2g. That's the force diagram. And the reason I have to say this is minus t is because it's opposite the positive direction, right? The positive motion goes forwards and down. So I have to say minus t, and m2g is the positive direction going down, equals m2 times a. So here I have, I'm going to ignore we ignore the second one there because there's no friction, otherwise we would build it in. Okay. So now let's solve for A and T. And there's an interesting way to solve for these. You just add both equations. So if you add the left side, you have T and negative T goes to 0 and you get M2G. And on the right side, you get M1A plus M2A. So we end up with, or you can solve it any way you want. You have two equations, two unknowns. So we have M2G, M1 plus M2 times A. That's when you solve these two. Leave room in your notes. If you don't see this, leave room and do it. Very crucial. So the acceleration, I'll bring this over to here now. We get acceleration equals M2G divided by M1 plus M2. One result. And what about the tension? The tension is just M1 times the acceleration. So now we're just going to multiply that acceleration by M1. The tension is equal to M1 M2G divided by M1 plus M2. Okay. It's nowhere near just as simple as M2 times G, is it? So that's the tension. So let's see if we can make some sense of these in terms of interpreting them, because the limiting cases, we can now deal with the limiting cases. For example, suppose M1 is 0. M1 is 0, then M2 is just going to be in free fall, right? M1 is 0, M2 is in free fall, and if, sure enough, we say if M1 is 0, we have M2 divided by M2, that's just 1, so A is just equal to G. So that makes sense. What if M1 is much, much larger than M2? Okay, we can go into the tension for that question. If M1 is much, much larger than M2, then the tension will approximately be M2 times G. I'm going to write those down. Note M1 much less than M2, then acceleration's approximately G. And if M1 is much greater than M2, then the tension is approximately M2G. Those are limiting cases. If you can study these, and this is approximate sign, right? If you can study these expressions and then figure that out, then recognize these, then you're in good shape. Because these are sensible ideas. You know, if M1 is too big to even budge, then the tension really will just be M2G, which is what we were expecting. But if they're moving together, the acceleration and the tension are different. Okay, the tension is reduced, as is the acceleration. Okay, very important problem. Now, sometimes a homework problem will give you a scenario like this and then ask how fast and how far. Okay. What that means is you found the acceleration, and now you can go into your kinematic equations and figure out those other questions. Okay. So those type of questions that ask about how far it goes in a certain amount of time, you always have to get the acceleration first. Then you can go to your kinematics and figure that out. Okay. In our lab, in the real lab that we're not doing this semester, this is often, or this is one lab activity that we have. And we actually do a number of things with weights hanging off the end of a pulley to provide a certain amount of force. So it's a very common scenario. And let me see what else. Here's something else we could note. So that answer that I just got right up here, I'm going to write it out. Equals m2g. Think of this as Newton's law again, is what it is. And what we have is the total mass. So the total mass, m1 and m2, provide the inertia. Okay. Remember, mass times acceleration is net force. The net force is only being provided by this hanging mass. So this really is mass, I'll give it a capital M times acceleration equals F net. So even though it's a two-body problem, you could have a three-body problem of this type. There's one in the book, maybe I'll assign it, and you would still have this kind of situation here. So both of these masses were providing inertia, but only one of them was providing force. So mass does more than just one simple thing. Inertia on the left side here, and then gravitational force on the right side. Okay. Let's check. Good, yeah, I'll assign a couple of these. This is how you set them up very carefully. Let's move on to fall with friction. An interesting topic. I can erase this now. Okay, so remember the hammer and the feather. I dropped the hammer, the feather, a couple other things to point out that we had to eliminate friction to discover the law of free fall. What we're going to do now is, now that we have the law of free fall and Newton's law of forces, we can bring friction back into play, okay? Because of course there is a lot of friction in the world. So fall with friction is our next topic. And instead of the feather, I brought something a little different. So these are coffee filters. You can make a good fall with friction demonstration. And are they going to fall at the same rate? Mark, get set, go. Hey, this side went faster. Maybe it was my hand. So I switched hands. Which side's going to hit the table first? This one's falling faster. It's interesting. They have the same cross section, so you can say they have the same friction, but this is 4 coffee filters and this is only 2. So this one has more mass. So if you have more mass with the exact same friction, it falls faster, okay? So let's go ahead and sketch that situation. Of course, our mass now is just going to be a square as usual. So this is fall with friction, M. Those are my coffee filters. I had, 2 M's on one side and 4 on the other. Let's go ahead and make this the positive direction is down. Just for simplicity, I'm making the positive direction down because that's the direction we're accelerating in. And now let's have mg, and here we have the frictional force. I'm just going to call it lowercase f again. So this is the weight, of course. This is the friction. And we have net force equals mass times acceleration. Positive direction is down, so apparently we have mg minus f is equal to m times a. Simple enough. There's friction pulling back against the weight. I'm just going to solve for the acceleration though. And when I solve for the acceleration, I'm just dividing by m. So here I get g minus f over m. Okay, this is already a fine little result. Simple, but what it's saying is, you see why I put the positive direction down. I just wanted to see that something is being taken away from the gravitational acceleration. So acceleration is gravitational acceleration, that would be 9.8 meters per second, g minus the friction divided by m. So you can see, if I have the same friction, I keep increasing the mass. You know, I had 2 coffee filters. I could make a stack of, say, 20 coffee filters, and it would fall much faster. And you see, I'm reducing this this quantity, f over m, by increasing m. So if the m is sufficiently large, the acceleration could just be like g. So suppose these coffee filters, now I have 6, but I put a big brick in them, or I put a lead ball on top of them, okay? Then they're just gonna fall like a lead ball, even though they still have the same friction. So when we were talking about eliminating friction, what we were really saying is we wanted to make this ratio as small as possible. So if we drop a brick in air, if this is small enough, then we say, yeah, the acceleration really is just like g. So yeah, just the basic, really basic discussion. We haven't put anything fancy in here. We can already understand fall with friction. The acceleration is slower. Now, we can take it another step. And I'll show you this coffee filter again. Let's just take one coffee filter again, or 1 or 2. Here's just one. Okay, we drop that. That's a little too wavery. Let's do 2 or 3. Here's a point I'm going to make. It very quickly reaches a constant speed and constant velocity. So within a few centimeters of me releasing it, it's just drifting down with a constant speed. What does that mean? That's called terminal speed. So when terminal speed, I'll call it v sub t, is constant. So if you have a constant speed, and I just showed you a constant speed for a ball of friction, that means the acceleration is 0, right? In fact, it's equivalent. If the acceleration is 0, then the speed is constant, vice versa. What does that mean? In our equation star, I'll name it star, in star, 0 equals g minus f over m. So that means the friction is just equal to mg. The friction is equal to the weight. So this is interesting for skydivers. So say you weigh 800 newtons and you're a skydiver. Skydivers reach terminal speed, okay? And then the frictional force on them is equal to their body weight. Okay. So again, the frictional force equals the weight of the object, and then you have terminal speed. So any of you who've done skydiving probably learned about some of this stuff already. And I think I'll give this one more little discussion point. I'll leave it right there for now. Terminal speed, friction equals weight. I'll write it down. We'll put a couple homework problems. And possibly start off with this next time as well. There's a little more to be said, but you can go pretty deep on this one. Yeah, so homework for lecture 13. We are in chapter 4, and I picked out a few. I may pick out a couple more. Let me check these out. Okay, I did 3 two-body problems, 60, 64, and 66. And it looks to me as though I just chose frictionless problems. You should thank me. Yeah. Okay, yeah. And not only that, one of these I did literally in class, and the other 2 are versions of it. They're two-body problems. So frictionless, sometimes I like to stick to the frictionless case so you really understand what's going on. Okay, that's good enough. We'll see you guys next time.